Well, it's time to talk temperature sensors, and let's get right into it. We're going to talk about type of temperature sensors, both analog and digital, and connecting those sensors to the Arduino. There are a lot of different ways to do that, and we're going to go into a comparison of the software required. Something a little different in this module. You will be doing some hands-on exercises with the sensors, but wait for it, no software writing. Do I hear cheers? Anyway, let's move on. We're going to be working with two of these sensors here, an analog sensor, and in this particular case we'll be working with a thermistor. There are also other types of analog sensors, RTDs and thermocouples, and then on digital we'll be working with a digital device, a one-wire DS18B20, and I've got a couple of other digital sensors there shown, and they use different types of digital interfaces, and we'll talk about those as we go on. So a thermistor, it's simple, two-terminal device that will vary its resistance with temperature. We set it up in a voltage divider circuit. So if you remember setting up a voltage divider with the potentiometer, this is the same idea. It's the same concept. We'll monitor the point between the fixed resistor and the thermistor, and as the temperature changes, the thermistor resistance will either go up or down. And they're very inexpensive. I mean, in the pennies a piece, and can be very small. Now, a couple of terms you'll hear when dealing with thermistors: NTC and PTC. Stands for negative temperature coefficient and positive temperature coefficient. With the NTC, the resistance will drop as the temperature increases, and with PTC, the resistance will increase as temperature increases. Both of these require calibration procedures. We just cannot read the voltage coming out and saying, oh, that's 25 degrees centigrade. You will need to do some fairly substantial temperature calibration and curve fitting for these devices. Temperature range runs from -40 to 150 degrees C, and a plus or minus 5% value is typical. Another type of analog temperature sensor is the RTD, resistance temperature detector. Again, it's a simple two-terminal device, and its resistance will vary with temperature. And again, you set up a simple voltage divider circuit, and you monitor the point between the fixed resistor and the RTD. Now, a little difference between this and a thermistor, and typically they have higher accuracy and repeatability than the thermistor, but it comes at a slightly higher cost. And you'll also need to be doing the calibration procedures. You get a little bit wider temperature range from -55 to 155, and a better than 2% error is typical with these. Another analog sensor is a thermocouple. And thermocouples are a lot of fun to work with, and you can have your students do all kinds of things with thermocouples. They can make little thermocouples, but simply a thermocouple are two different wires that are insulated from each other, and when they come out at the end, you take them, twist them together, and make a junction. And the metallic differences between those two wires at the junction generates millivolts that are correlated to temperature. And with the thermocouples, you can get a very small contact point. Again, you're just two small wires put together, and very fast response time because of the limited thermal mass associated with the two wires that are connecting to your temperature point. There are some problems with thermocouples, and it's difficult to interface for accurate measurements. There are things like cold junctions, and when you connect up your wires, dissimilarities are introduced, and those connection points can introduce small offsets in voltage that will affect your temperature reading. So there are interface chips out there specifically designed to connect thermocouples to analog to digital converters, but we're going to stay away from those for right now. Nice thing about thermocouples is the temperature range, well over 1500 degrees C. So at the beginning of this presentation you saw a picture of a ROV inserting a thermocouple temperature sensor into a black smoker, and with the temperature of that on 600 degrees centigrade, it's way higher than we can do with those other sensors, and so we're pretty much forced to use thermocouples for this. Now talk about digital temperature sensors. We have a one-wire device that we'll be using, the DS18B20. Very simple device. It only needs one wire plus ground for communication, and in a pinch it could be powered from that data line. So you really need two wires to power it up. We'll be using three. We'll provide it with power and then take its extract its data from it. It's accurate, plus or minus ½ degree C over the range of 10 to 85 degrees C. And it will measure minus 55 C to plus 125 degrees C. Now here's the nice part about digital temperature sensors. They're factory calibrated. You don't have to mess with calibration. They're calibrated from the factory. What you read is what you get. And it's typically 750 milliseconds for a 12-bit conversion. And your power supply range, very nice wide range of power supply from 3 to 5 volts. Now there are other interface standards that are used, and I'm putting these up here because there's a lot of Arduino code out there to use these other interface standards. And I2C or I2C, that's an interface where you can have multiple sensors on the same communication wires, which is very nice. You can put a string of sensors measuring temperature and go out and read one at a time to retrieve your temperatures. You can see the accuracy there, again factory calibrated, a little faster conversion time and a little wider power supply range. Finally, there's another interface, digital interface called an SPI, and with this part we've got an ADT7310 8-pin device. Very good accuracy, and this is a 16-bit converter, so you get very fine temperature resolution. Again, factory calibrated, conversion time 240 milliseconds. And with this, since you're working with SPI, we're going from kilobit, 100 kilobit per second transfer rate on I2C to up in the megabit per second transfer rate with SPI. And the power supply range is 2.7 to 5.5 volts. Now connecting the analog sensors, they are the simplest by far and away. It's really hard to argue with connecting a single wire to an Arduino and sampling away. You already know how to do the voltage divider samples, but you have accuracy and calibration considerations. The other thing, since there is only two wires, they're extremely easy to waterproof. You can run those two wires out of the ROV, make sure they're sealed where they go out of the ROV, and run those wires off and seal the ends up and put your sensor out at the end of a probe or something. Because they're small, their temperature reaction time is going to be excellent. Very small settling time. You have a change in temperature outside the environment and it will react quite fast. Problem with accuracy, it's only as good as the least accurate component. So if you use 10% resistors in your voltage divider or other things, that will affect your sampling and your accuracy. And then the long wires between the sensor and the sampling point, which is your Arduino, can introduce errors and provide a way for your electronic noise like motor noise and other noise to couple into those wires and distort the measurements. If you want a very quiet environment, you might extend those wires with shielded cable or twisted shielded cable to reduce the possibility of electronic noise entering in and affecting your samples. Here's the thermistor connection to the Arduino, and you can see we can do this with two wires out to the thermistor and bring the connection point between the thermistor and the pull-up resistor, the 10K resistor here. You take this connection point and bring it over to one of the analog inputs. Here it's shown in analog input 0. We can bring it into 1, 2, 3, whatever it is we happen to be using. Very simple. And as I mentioned earlier, if you were to extend this for any length, you should use a twisted pair wire that is also shielded to provide as much noise immunity as you can. If you are concerned about noise and possibly spikes coming in and damaging your Arduino, you can go back to the analog section where we talked about analog input protection and put the diodes and everything there on the inputs. Now if we connect digital sensors to the Arduino, we're going to need 2 to 6 wires depending on the type of interface. And with multiple wires, it always increases the waterproofing difficulty. And if you put too much waterproofing on the chip, it'll increase the time for accurate temperature measurement. So whatever waterproofing you put on there, you want to keep it as thin as possible. Make sure it will still cover and still insulate, but not provide this big thermal blob that has to warm up or cool down depending on what the case may be. I don't think you want an ROV sitting there for 5 minutes waiting for a temperature to stabilize. One nice part about this, accuracy is not compromised by the waterproofing, just the response time. And longer wires in some cases can be handled by slowing down the acquisition or the clock speed, allowing for the signals to settle. And the conversion is performed at the sample site, reducing external sources of error. And the digital interface preserves the accuracy of the sample. So here's a simple one-wire diagram that you're using. This is the sensor we'll be using. We have +5 going to it and ground. And then here we're showing it going to IO3, but you'll be wiring it up to another input pin later on. Simple 2 or 3 wire interface. This sensor can go into the mode where you can power it whenever the DQ line is held high by the processor. Here's an I2C diagram. The Arduino has built-in I2C interface and routines, and it takes 2 wires to go out, and it's a data line and a clock line. Nice part about this interface is you can put multiple sensors in parallel off of those 2 lines. So if you look over here where it says A0, A1, and A2, that's the point where you would differentiate the sensors. One of them would have the code for 0, another one would have a code for 1, another one would have the binary code for 2, and so on. With 8 different sensors can be shared with this on this line here. SPI is nice because of the high speed. Instead of the kilobit per second transfer rate, you can transfer rate at megabits per second. Very similar, you've got a clock line, data out and data in, and a chip select. Now if you want multiple sensors, you can put the S clock, D out, D in lines all in parallel between the sensors and provide them with individual chip select or CS lines, and that'll allow you to read each sensor individually.